Hey everyone, back here. It's your friendly neighborhood math teacher, Mr. Bennett. Today we're covering lesson 5.2. And as you can see at the top, our question is going to be who will win the last banana? And so for today, we have a scenario which is suppose we're on a desert island playing dice with another castaway. So you guys have been lost at sea. It says the winner's prize, playing dice, will be the last banana on the island. Okay, so the winner gets to eat the last banana, the loser gets nothing. Sorry. So here are the rules of the game. Each player is going to roll a single dice. Okay, a single die. That means there's going to be a total of 2 die, right? Each person rolls one on their own. Between the two of them, if the largest value is a 1, 2, 3, or 4, then player 1 wins. If we roll both die and the largest number is a 5 or a 6, then player 2 wins. So what I want you to do right now, given that scenario, is number 1, who do you think has the advantage in this game? Do you think it's player 1, player 2, or neither of them? So go ahead and pause the video and just make your best guess, okay? And try to explain why you think it's player 1, player 2, or that neither of them have a real advantage. Okay, I will kind of share with you what I would think in this scenario in just a second, but try to see what you can come up with on your own. Who do you think has the advantage? So go ahead and pause this and write down that answer. So for me, I think it would be pretty clear that player 1 would have an advantage here. Because ultimately, there are more ways for them to win, right? Like, in my opinion, all they have to do is have a high number of a 1, 2, 3, or 4, and they get to win, versus only 2 options for player 2. Okay, so there's 4 options for player 1, only 2 options for player 2. And so I would think that player 1 would probably have the best advantage in this case. Okay, so you're going to play this with a partner, so find somebody next to you. You guys can pause the video in just a second. And you're actually going to play this game. And so all you have to do is go into Google and just type in dice roller. Okay, if you do that, I'm going to kind of refresh this page here. It'll pop up with 1 dice. All you have to do is, if you look underneath that dice, there's a bunch of die underneath it, a 4, a 6, 8, 10, 12, and 20. If you click on the 6 once, it'll add in a 6-sided die. And so now that you have both die, you're going to click roll. So the highest number in this case was 2. And so I would give that up to player 1. So player 1 won that time. And if we go back to our die, roll again. This time, highest number was a 1. Player 1 wins again. Okay, one more time, we're going to roll. Highest number was a 6. So since the highest number was a 6, player 2 wins this time. Okay, so find somebody next to you. It's just kind of fun. And record your data. Okay, play this. It says 20 times. Go ahead and play that 20 times and see out of those 20 how many each of you gets. Okay, so at this point, if I stopped, I would have 2 out of 3, and this would be 1 out of 3. Okay, the proportion would be 0.67 and 0.33. Okay, so do that 20 times and see what you guys get. I'm going to continue as if I had done this 20 times with a partner, just so I have some data to work off of. But if you want to pause it now, try it for yourselves and use your data, that's totally fine. So let's just say I continued on with a partner, and player 1 ended up winning 3, 4, 5, 6, 7, 8 times, and player 2 ended up winning 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times. So I have 8 out of 20, which is 0.40, and 12 out of 20, which is 0.60. So if we look at this, who actually won more often? In my particular case, it was actually player 2. Okay, yours might have been different, and that's okay. But we're going to say, so again, if everyone does this 20 times, total of, I don't know, 15 or so of you guys. Let's just throw out, let's say we had a total of about 300 times. So obviously we're not there in person to actually get all of the class data. So I apologize for that. But let's just say that player one won 126 out of 300 total times. Okay, we ran this a bunch of times, and we got 300. Okay, which is about 15 groups, which is about 30 students in a class. So yeah, that's about right. Okay, about 300 times. And of those other 300, 174 were player two wins. Okay, so what are those proportions? Again, just use a calculator, find the decimal. 126 divided by 300 is 0.42. And this other one would be 0.58. And what we want to remember here is we did this a lot of times, right? It'd be one thing if like, hey, I played dice the one time versus if I did it 300 times. And so that's big in this case because that's referencing back to our law of large numbers that we just talked about in 5.1. Okay, that idea of the more simulations we run of a sample of this, the more samples we have, the closer we're going to get to that true percentage. Okay, and so in this case, it wasn't just a one-off, could have been random, could have been really high, really skewed one way or the other. After doing it enough times, a bunch of times, we kind of start to get an idea for what that real percentage actually is. Now, number 4, to determine the true probability of each player winning, we could list out all possible pairs of rolls that we get. Complete the table. So again, we could roll a 1 and a 1. We could roll a 1 and a 2. We could roll a 1 and a 3, a 1 and a 4, a 1 and a 5, a 1 and a 6. And I'm actually going to change all of those to black. I'm sorry for not doing that ahead of time. And in our second row, right, we could roll a 2 and a 1, a 2 and a 2, 2 and a 3, 2 and 4, 2 and 5, and 2 and 6. And so at this point, if you want to skip ahead, I don't know, probably 15, 20 seconds or so, I'm just going to fill in the rest of the table. I think you kind of get the picture now. But that's what we're going to do here. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, and 3, 6. 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6. So we have all those different possible combinations of rolling two dice. So letter A says, what is the probability that player 2 wins where the largest value of 5? And so what we're looking at here is basically, why is that an arrow? Okay, sorry. We get a possibility of 5s here, right, where the highest number is a 5. Because if I go one more to the right, the highest number would be a 6. But we also get these options here. So that probability, how many outcomes is that? Well, I see 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 out of a total of, I've got a 6 by 6 grid, so 6 times 6 is 36. So we have 9 out of 36, which would be a 0.25, 9 divided by 36. And this is what we're going to call the probability of getting a 5. Now part B says, what is the probability that player 2 wins with the largest value of 6? Well, that would be all of these. And we're going to change the fill color there. Whoops. Which would be this L shape on the outside. And so how many possibilities is that? So again, you're just counting them up. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 out of 36, which again, if you put that into your calculator, I'm going to do that off screen here. 11 divided by 36. I have 0.31. So I have 0, 3, 0, 5, 5, 5, bunch of 5s. So we'll just do 0.31. And that's the probability of getting a high number of 6. So now question C says, what is the probability that player 2 wins, just in general, right? Regardless of whether it's a 5 or a 6, right? What is that probability? And so in this case, player 2 winning is a 5 or a 6. And so we want to think about this as, what's the probability of getting a 5 or a 6? And so in this case, the probability of getting a 5 was 9 out of 36, plus the probability of getting a 6, which was 11 out of 36, which is a total of 20 out of 36, which is, again, calculating off screen, a 0.56. And so now question D says, what is the probability that player 1 wins? So what would need to happen for player 1 to win? Well, a 1, 2, 3, or 4. And so that would be these squares all in here. And I will fix that fill color in a second. I know it's bothering you as much as it bothers me. Fill. Orange? No. Orange? No. Oh no, where is this orange color? Oh, it's over here. There we go. And that's now going to bother me. Okay. Sorry. So basically all of the orange is what player 1 could win. So in this case, if we count those boxes, got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 boxes out of our 36. So 16 divided by 36 is 0.44. And so one of the other ways we can also think about this, not just simply counting, thinking of it as, okay, player 1 wins by it being a 1, 2, 3, or 4. Another way we could think about this is player 1 wins when it's not a 5 or 6, right? So we can basically say that player 1 winning is what happens when player 2 does not win. And I know that might seem like really basic, like that might seem like that's a really easy and like duh kind of statement, right? That player 1 wins if player 2 does not win. But that's a really key idea in this lesson, that we can look at things in terms of a not event happening. So it's this event or it's that event not happening. Okay, and so we're going to kind of cover that here in a moment. But that's another key idea. Okay, I just want to start planning in your head as we move into our notes. And so that's it for the activity part of that. Pretty straightforward, pretty simple. So for our basic probability rules here, our first learning target has to do with a probability model. And this shows all possible outcomes and the probabilities or probability of each outcome. So each probability has to be between 0 and 1, right? 0 means that there's 0% chance of happening. 1 means there's 100% chance of happening. So it's got to be somewhere in between. And all of the probabilities must add to 1, right? Ultimately, all of the different possible outcomes, if I take all those possible outcomes and add them all up, it should be 100% of the outcomes, right? All of the outcomes added together gives me 100% of the possible choices or the possible results that we could have. Learning target number 2 has to do with something called the complement. And so the complement, we say the complement of A, right, event A, okay, something happening. For example, rolling a 5 or 6, okay, would be an event. So the complement of A, it's not complement, right, which is what you say to somebody when you want to say something nice about what they're doing or saying or wearing. This is a complement, and the complement of A is A with a little c. Okay, the little c stands for complement, which is the event that A did not happen. So A is that event happening. The complement of A is that event not happening. And so the probability that A complement happens, right? The probability of A not happening is 1 minus the probability of A happening. So basically what this means, I know it seems a little funky, But basically all this means is this, right? Let's just say that event A it's raining. Okay, what's the probability of it raining? Well, let's say that probability of it raining, you don't have to write this down, but the probability of it raining is 60%. Okay, that's rain. So if the probability of event A of it raining is 60%, what is the probability of it not raining? Well, that's the other 40%, right? 60% says it is going to rain. The other 40%, because 100% means something's going to happen, right? 100% guaranteed something is going to happen. So it's either going to rain or it's not going to rain. And so if it's 60% chance of rain, that means 40% of not raining. And so how do we find that? Well, technically, and we do this in our brains, we don't think about it, right? But 100% minus the 60% chance gives us the 40. Okay, so that's basically all this is saying, is that if I know the probability of A happening, then the probability of it not happening, I just subtract that percentage from 100. Okay, which as a decimal is the number 1. Okay, so that's what this is saying. You can write that down if you want, but you don't have to. Okay, as long as you understand what a complement is. And then lastly, learning target number 3. Is about mutually exclusive. This term right here is kind of big. Okay, we'll see this throughout the chapter. Mutually exclusive. 2 events, could be more, but typically just 2 events, are mutually exclusive if they have no outcomes in common. Basically meaning can't happen at the same time. And so what we can say from this is that the probability of event A happening or the probability of event B happening is the probability of A plus the probability of B. If I know they are mutually exclusive. If A and B can't happen at the same time, then the probability of one or the other happening is the probabilities added together. So an example of this, if I think about rain versus not rain, I'm going to kind of scroll back up to that example. Okay, it cannot rain and also not rain at the same time. Either it's raining or it's not raining. Cut and dry. Okay, raining or not raining. And so since they can't happen at the same time, raining and not raining are mutually exclusive. And if that's the case, then what's the probability of rain or no rain? Well, the probability of rain is 60%. The probability of not rain is 40%, which would get us up to, add them together, 100%. Right? So what's the probability of it raining or of it not raining? Well, 100%, because it's either going to rain or it's not going to rain. One of those two things is going to happen. Okay. In the case of our activity, one of the places we looked at this was letter C up here, number 4. So what is the probability that player 2 wins? right? We had the probability of 5 or a large number of 6. Now, could they get a 5 and a 6? Yes, but remember, if they get a 5 and a 6, that is considered a 6, right? Because we're only looking at the largest number. And so could they technically roll both of them? Yes, but that would only count as being a 6. Okay, so in this case, these are mutually exclusive. Having a high number of 5 and high number of 6 are mutually exclusive. I can't roll 2 dice where the highest number is a 5 and also the highest number is a 6. Doesn't make sense, right? The definition of saying highest number is there's one that's not bigger. And so it either has to be a 5 or the highest number has to be a 6. And so since they are mutually exclusive, the probability of 5 or 6 is the probability of 5 plus the probability of 6. Okay, now the other thing was that idea of a complement. And so where we saw this earlier was in part D, we kind of briefly touched on it. And that was the probability that player 1 wins. Another way of thinking about that is that player 2 is not winning, right? That it's not a 5 or a 6. And so in this case, if I say that event A, or let's just say I have the probability of player 2. The probability, I wrote that wrong. The probability of player 1. The probability of player 1 happening is the same as the probability of player 2 not winning. And so player 2 not winning is what we would call probability of player 2 complement. And according to my rule, the complement is 1 minus the actual event. So 1 minus the probability of player 2. So the probability of player 1 happening is also the same as saying the probability of player 2 not winning, player 2 complement, which is 1 minus whatever player 2's probability is. And so what that looks like would then be 1 minus the probability of player 2, which was 0.56, which gives us 0.44, which matches what we found earlier, right? So they're just kind of two ways of thinking about the same scenario. And in this case, it wasn't necessarily hard to find the probability, just figuring out how many opportunities they had. But if this was like a really big data set, right, where we had more than just 36 numbers to look at, like let's say we had, 1,000 that we needed to sift through. If I find the probability of player 2, right, if I do it for one of them, then I have a lot of information that I can use to then find more about player 1. Okay, that's kind of the end goal here. It's not so much that it's going to always replace that first thing we did, but that it could, if we have a really large data set where that would just be a lot of work to do both of them. Okay, and I know it's a little bit weird, so if you still feel like you don't quite understand that, please ask, okay? Because the compliment thing is always kind of tricky. This one seems to be one of those things that's a little bit difficult to understand. So if you have questions, if you still don't feel like you're quite getting that, ask me about it, please. The next time I'm in class, where you can come in at lunch, please ask, because that's kind of a big concept as well. Those two things being a complement, right? An event not happening, as well as two events being mutually exclusive. Okay, that's going to come up over and over again in this chapter. So I want to make sure you guys feel good with that. Okay, so if you've got questions, let me know. Otherwise, that's it for this lesson. I hope you guys had fun, enjoyed your time. Remember to hit that like button, smash the subscribe button, all that fun YouTuber stuff, because of the algorithm, YouTube machines thing. And yeah, I'm not going to be a famous YouTuber. That's probably not going to happen because nobody really likes looking at math stuff on YouTube. But I hope you guys have a great rest of your day. If you guys have any questions, reach out, let me know. And otherwise, I will see you guys next time. See ya.